Hello again, welcome back to ME4111. This is Engineering Mechanics 1 Statics, and we're working through George Sheet 5 and currently gone on to question 9. And in this question, we're looking at friction. So it starts with a 2D problem, and just get us working on that. So we've got this 60 kilogram bar AB. So let's go from there up to there. And so we'll have a mass of that of 60 kg. Got a force P pulling it, so off that way, with smooth guides at B, right? So that means the smooth guide means that it's free to move in the vertical Y direction, or up or down, but it can't move laterally. So this thing would, if it's going to move, it's going to slide down. So this would extend out when P is pulled. Okay, and we're told the coefficient of static friction at A is 0.8. So we've got a coefficient of friction along here. And this is smooth, so it's free to roll. It's well-oiled bearing, so that there's no friction there, essentially. So we're told if P is 400 newtons, find the friction force at A. Okay, so we're told this is 400. We want to know what is the value of the friction force at point A. Okay, so our first approach is to transform this into a free body diagram. So we're no longer distracted by this. Again, I've drawn the system in isolation, so the bar AB. And I don't have any contact shown. So again, there's the guide is not shown, the surface here is not shown. And I now put on my forces, so I have P acting on it. As shown, I have the weight acting at the center of it. I have a reaction force at B. There's none in the vertical direction because this thing is free to move, so it doesn't react in the Y direction. But if I try and pull it in the X direction or push it into the wall here, so if I try and push it in that way or pull it out this way, this wall, these surfaces are going to stop that motion, so I'll have a reaction force. Okay, and what I've done is I've indicated that B is acting in this direction. My logic for this is that P is pulling it out, so chances are that B is going to come from this surface. It's been pulled into the surface, so chances are it'll react that way, and there wouldn't be much of a reaction force there. So the net reaction force is that way. In effect, there's two because there's two contact points in the variance, but we're just going to treat it as one combined reaction force. All right. At point A, then we have, it's a rough surface, so we have the wall normal reaction, so R, and then we have the friction force. And again, I'm anticipating that the motion will be in the positive X direction, so friction will be acting against that to resist that motion. Okay. So what I'm going to do is I need to calculate the friction force. So what I'm going to do is I'm going to assume we're in equilibrium, and then figure out if the friction force is at or below the maximum value it can be. And if it's less or at that, it is the value I've calculated it to be. But if it's more than that, then the thing is moving. Okay, so I'm going to start with this assumption of equilibrium and then verify that assumption. Now the sum of the forces equals 0 and sum of the moments equals 0. So looking in the Y direction, I sum the forces in Y equal to 0. So I have minus W plus R equals 0. And straight out, that gives me the reaction force. R is 588.6 newtons. Okay. The next thing I can do is I want to get F. So if I take moments up here, I would have a moment due to W, a moment due to P, a moment due to R, a moment due to F. I have R, W, and P, and that will give me out F. Okay, so again, I'm planning what I'm doing based on my governing equations and my free body diagram. Okay, so taking moments about B equals 0. So I have P times L over 2 sine of 60. So L over 2 sine of 60 is this distance here. Okay. Then I have minus W L over 2 cos 60. So again, W. And the distance here is this distance. So that there is L over 2 cos 60. And again, that's going to swing it in a clockwise direction, which is negative. So that's why I have the minus on it there. The next force then is the friction force. So F is going to swing it again in a clockwise direction. So I'll just clear that a second, just change the color. So there we go, blue. So this force is going to swing it around this way. So F will. And my distance is this distance here. Okay. All right, so that's the distance from where I'm taking the moment to the line of action of the force. So I have that. And then the last one then is RL cos 16. Again, you should, that's the distance should be obvious on that as well. So we have this distance here. That's the distance from line of action of the force. And again, it's going to swing it in a clockwise, sorry, an anti-clockwise direction, which would be positive. Okay, so that gives me this equation. And then I just work that out. And I can see that I get the friction force to hold this in place is 369.9 newtons, so 370 newtons. Now I want to check this value because this is the value I need to hold it there. I want to check this value against the maximum value. The maximum value is mu s times r. And I have the reaction force already. I have that from the previous slide, so I worked it out here, 588.6. So the coefficient of static friction is 0.8, so 0.8 times 588.6 gives me the maximum possible value of friction is 470.9. And you can see that comparing those two, this value is less than that. So therefore, my assumption for equilibrium is valid because the system can produce sufficient friction to hold it there in place. Okay, so the value of friction is what is required. So it's the 370 in the direction shown in the free body diagram because my answer cannot be positive. So it is going the way it's pointed there. Okay, the second part then is to find out P when the friction is maxed. So how about decide that? What value of P is required for slip to occur at A? So the maximum friction force I can produce here is F max. So at F max, this will still be in equilibrium. But if I increase P anymore, then the friction force won't be able to match the required friction force to hold in equilibrium. So that's my limiting value. So if I solve this for P as an unknown when I'm at the maximum friction force. Okay, so that's my method of attack. So I need P when F is equal to F max. So again, I'm just using the same approach there to work out P. The reaction force hasn't changed. So again, you just need to be careful of that. If P had any kind of a component down like that or a component up like that, then the reaction force would change. Okay, so just be careful of that. My W minus W plus R equals 0 equation doesn't change by changing P. But if this had any vertical component in it, that would cause the reactions to change. Okay, so just be conscious of that. Don't assume that automatically. We've seen that in the aircraft example already. Okay, so by taking moments again at point B, I have my moment equation now. P is not known, but I know what F max is. Okay, whereas previously I knew what P was, I didn't know what F was. So I can solve, and I get P is equal to 602 newtons for that. Okay, so that's the second part of the question. Okay, that's that, and we'll move on to the last question next.